So today I'm going to talk about probing of coherent nuclear wavepacket dynamics with X-ray emission and scattering. So this is a work I did as a postdoc at Pulse Institute at SLAC National Accelerator Laboratory at Stanford in the group of Kelly Gaffney. Why it's not okay. The talk is mostly about two of recent papers. So the first one that we published in Nature Communication is the beginning of this year, and recently we had a follow-up paper in structural dynamics, where we mostly focused on the calculations that we did. So the brief outline of my talk is that I kind of have two themes. So I will first talk about mostly the photo-induced electron transfer dynamics in these iron photosensitizers that we investigated. And this concerns about using X-ray emission and X-ray scattering simultaneously to probe the structural and the electronic dynamics. And in the second part of my talk, I mostly discussed how the X-ray emission spectroscopy is sensitive to the structural dynamics, and in particular coherent nuclear wavepacket dynamics, and how this emerges in ultrafast experiments. To start with some brief motivation. So the motivation, the general motivation for these investigations comes from the solar energy conversion science and utilizing light to, for example, generate electricity or synthesize solar fuels. For example, in the applications of dye sensitized solar cells, or for example, in case of photocatalysis and hydrogen evolution, water oxidation. So the central challenge in these fields is like how to design materials that can efficiently capture light and transform this light and solar energy into, for example, electricity, or in chemical compounds that can be used for fuels, for example. So important part in harnessing solar energy is the photosensitizers, that are the molecular units that capture light. Conventionally or traditionally, the most common molecular photosensitizers are based on noble metals. So, for example, very common photosensitizers are ruthenium based. So these ruthenium photosensitizers, when they absorb light, the electron is transferred from the metal to the ligand. And as this electron is on the ligand, this molecule can drive photochemistry or photoredox chemistry. So what in the recent years now, several different research groups have been pursuing is trying to change the expensive and scarce noble metals like ruthenium with more earth abundant elements, for example, iron. So iron is one of the most earth abundant metals in the world. So it would be very attractive. You use, instead of ruthenium, isoelectronic iron, and use, for example, so the picture that I'm showing here is ruthenium tris-bipyridine and iron tris-bipyridine. So used instead, for example, iron tris-bipyridine to drive photoredox chemistry. Unfortunately, as it is well known, contrast to ruthenium tris-bipyridine that has a very long metal to ligand charge transfer excited state, lifetimes, around 600 nanoseconds. In case of iron treated by pyridine, the lifetimes are on the order of 100 femtoseconds. So this means that very rapidly, the metal to ligand charge transfer state relaxes back to the very low energy metal-centered excited states that are not able to actually drive any photoredox chemistry. And effectively, you're just generating your light into heat, not into usual, not transforming any chemical bonds. And recently, some of this research has been also, like, there has been a nice review paper by Oliver Wenger titled "Is Iron the New Ruthenium?" Where he summarizes some of the recent developments. And of course, the question that emerges from here is that we need to better understand the photophysics in these transition metal complexes and in iron photocomplexes in particular. In recent years also, there has been, particularly by the group, there's been a large synthesis effort, particularly in the Lund University, but in the group of Kenneth Wellmark, where they have synthesized not polypyridyl iron complexes, but iron complexes that they call iron carbene complexes. So in these iron carbene complexes, instead of pyridine ligands, they also have ligands, aromatic ligands, nitrogen heterocyclic aromatic ligands that they call carbene ligands, that instead of nitrogen, they bind with the metal with the carbon. And this metal ligand interaction is much stronger, and the motivation is that this will lead to a higher, longer metal to ligand charge transfer lifetimes. So a few years ago, for example, they also demonstrated that using the complex, the iron complex, like showed here, slightly its modified version, they were able to convert 92% of the electrons they were able to inject to a titanium oxide substrate. So here the question again is, okay, what is different in these iron carbene complexes and what makes them more efficient photosensitizers? And this is the complex that we investigated in this work, and we were trying to figure out, okay, what are the excited state lifetimes, what are the relaxation pathways in this complex, and what makes it more efficient photosensitizers than the traditional iron polypyridyl complexes. So the experimental methods that we used, first, of course, we used iron K alpha and K beta X-ray emission spectroscopy. I believe that many of you have heard about this technique, but I just very briefly summarize. So why we use this, and in particular, for example, iron K beta X-ray emission spectroscopy, is that they are sensitive to the spin and oxidation state of the iron. So in case of iron K alpha spectroscopy, we are observing the decay from or the filling of the 1s hole from the 2p level. In the case of the K beta X-ray emission spectroscopy, we are following the filling of the 1s hole by a 3p electron. And although these electrons are not directly involved in the bonding, there are electron-electron correlation interactions that interact with the 3D electrons, and hence they're sensitive to the occupation and the spin state of the 3D levels. So there has been several reviews, and I also recommended to look at the Sara Lafluenza talk 2 months ago, where she actually talked about in a very nice way in the detail how these spectroscopies are actually sensitive to the spin and oxidation state, and actually not only the spin, and this is also something what I will talk about. So the crucial for this study is that here, if you look at the spectra on the right of the iron K-beta X-ray emission spectra of some model complexes that have a different spin and oxidation state, you see a clear sensitivity. And in particular, for example, if you have a high spin, if you generate a high spin iron complex, you see a rise in this K-beta prime feature. So simultaneously with X-ray emission, we used also ultrafast X-ray solution scattering. So X-ray solution scattering is a probe that is directly sensitive to the nuclear dynamics in solution. Development of this method has been carried out by several research groups, importantly Michael Wolf in ESRF, Ihi in Korea, and Martin Nielsen, who is our collaborator at DTU University. What is important for the solution scattering is that this is sensitive globally to the molecular structure of the molecule, and it is also sensitive to the solvent environment and solvent heating taking place during the reaction. So typically we use this kind of a decomposition scheme where we utilize the fact that our solute contains heavy atoms, and for that reason we can separate the solute dynamics in combination with the DFT calculation. We can separate the solute dynamics from the solvent dynamics and actually learn about how the solute structure evolves during the photoreaction. So here is a brief sketch of the experiment. This is a standard experimental configuration at the LCLS, at the XBP beamline and at the XAS beamline. We used liquid jet to deliver our sample, so our molecules that were solved in acetonitrile. This sample was then excited by 400 nanometer laser light and probed subsequently with a big beam of X-rays at around 8.5 kilo electron volt. So in the downstream, we had a large two-dimensional CS pad detector to detect elastic scattering, elastic solution scattering. And in this experiment, we actually used two spectrometers. So we had one HAMOS spectrometer to capture the iron K-beta X-ray emission. And in addition, we also had Roland spectrometer to capture the iron K-alpha X-ray emission at a single photon energy. So on the right side, you can see in principle the data that we collected during our experiment. So we have three data sets. So we collected simultaneously X-ray solution scattering, shown here. Also, we measured the transient spectra of K-beta X-ray emission scattering, and we measured K-alpha X-ray emission at the single emission wavelength. So you can also see from this data already that we observe this kind of oscillatory signals in X-ray solution scattering and in X-ray emission. And this is in addition to the slower dynamics that we relate to the population changes in the molecule. So I will first continue with discussing the population dynamics, and in particular I will use K-beta X-ray emission data to analyze the population dynamics. So here are the delay traces of the K-beta X-ray emission. So now I have just taken in principle a cut or a scan from an energy range from 7056 eV to 7058.5 eV. And what we observe here is, if we analyze carefully this delay trace, is that the dynamics is not single exponential, it's actually a double exponential. And the kinetic model that we can use to describe this dynamics indeed includes first excitation to the metal to ligand charge transfer state, which in a very fast time scale, in around 100 femtoseconds, branches into two states that one is also a MLCT character, and the second one is a character of a triplet metal-centered excited state. So we don't, in this complex, different, for example, from iron 3-spy pyridine, we don't see any population of quintet metal-centered excited states. However, we do see this population of triplet metal excited states. And this we can rather robustly say from the spectra of the K-beta X-ray emission. To analyze now the X-ray solution scattering signal, this is, in general, it's a complicated task because it involves many different overlapping sources of signal. For example, the structural signals of the triplet metal-centered excited state, the metal to ligand charge transfer excited state, as well as the solvent heating signal, they are all overlapping. So in order to carry out this analysis of the X-ray solution scattering, we use a global analysis scheme. So in this scheme, we first use a singular value decomposition of the two-dimensional scattering signal to separate it into the principal components of scattering curves that evolve in time. And then we use the population kinetics that we have derived from the X-ray emission. We actually we fit the time traces of the time vectors of the X-ray scattering signal to the kinetic model derived from the X-ray emission. And by fitting this, we can, by using the relative amplitudes, we can construct actually the X-ray solution signals that corresponds to the individual electronic states. So using this kind of global analysis of scheme and decomposition, we can eventually assign a specific structural signatures to these electronic excited states. Although in the X-ray solution scattering, they are overlapping, but using the dynamics from the X-ray emission, we can disentangle these different components. In general, now that we have, if I go slide back, now that we have these scattering curves to actually extract, for example, specific bond lengths, specific solid bond lengths from the scattering curves, it's not a simple task in itself, and usually we rely significantly on the DFT simulations to do that. So in this work, we mostly focused on analyzing the structure of the triplet metal-centered excited state, because as we find that this is the structure that is actually oscillating or coherently oscillating, and using the DFT simulations and just using a very simple model of coherent oscillations on a single surface, we can qualitatively very nicely simulate the shape of the X-ray scattering curves that correspond to the motions, or let's say the breathing motion of the molecule as it expands and contracts on the triplet metal-centered excited state surface. So this is something we can we can extract from the experiment, is that it is the triplet metal-centered excited state that is breathing coherently. So with this, I actually come to the kind of the end of my first part of my talk. So I kind of showed that we see this rather non-trivial population dynamics. So we have a branching, we have an ultra-fast population of triplet metal-centered excited state, and we also have a coherent motions on the triplet surface. So we find that significant part of the population that we excite, around 60%, actually lives in the metal-centered, in the metal to ligand charge transfer state, around 10 picoseconds. So this is significantly longer than, for example, in iron 3-spy pyridine. So actually 100 times longer, right, than the charge transfer lifetimes in iron 3-spy pyridine. So we think that this is the state that is able to drive the photochemistry or photoredox chemistry and donate electrons to the titanium oxide surface, for example. And this kind of branching dynamics, this is actually not the only, so in principle, we don't know exactly why this branching happens. We do know that it must be related to somehow the hot charge transfer state and how this relaxes. And we also know that we have also observed these dynamics not only in this complex, but also another similar iron carbon complexes. And we also know that the group in Lund, they have been already been successful, for example, in improving these iron carbon complexes further, and even they have been extending the lifetimes even further. So Jerry, I think I could take some questions.
All right, there's a few. First, if you can go back to the slide that shows your K alpha, K beta, and the scattering all together.
Yes. Oh, I'm going forward.
You're giving away the mystery.
Yeah, I know, I gave it away.
All right, everyone can go. You've seen the rest of the slides. You never talked about the K alpha.
I am going to talk about K alpha.
Okay. Well,
yes.
I guess since you showed this anyway, I'll ask the question. Were you sitting on the peak of the K alpha one, or off to the side to look for a change in the width coupling to spin?
So we are sitting on the maximum of the K alpha in principle. So it's not the photon energy that is actually the most sensitive to the, for example, spin state or oxidation state. It is just the one photon energy that we chose during the experiment, and we went to the maximum of the ground state and we measured there.
I see. Okay, I had wondered if maybe you were sitting on the steep part of the peak, so you'd be more sensitive to shifts or broadening.
Yeah, this is definitely true. That right. Ideally, you would want to measure also K alpha as a two-dimensional. right? Because yes, there is a steep part, and it's very sensitive where you exactly sit. How big
Okay,
is the difference?
that's fine. Jacinto, you had a question?
Yes, can you hear me?
Yes.
Yes.
Yes. I found the coherent time fairly large considering the dynamics of the system. I mean, everything decays in about 1.5 femtoseconds. Everything gets decoherent in less than 1 femtosecond. So why the periodicity of almost 300 femtoseconds on an electron wave packet? I mean, that's very large, I would say.
Okay. I mean, the coherence we observe is a nuclear coherence.
Okay.
So it's not, of course, it's not electronic coherence. It's just a coherence of different vibrational states of in principle, the iron ligand breeding mode, right? So the coherence that we observe is purely a nuclear coherence, and this is something that has been observed now in several studies, right? That you have nuclear coherence that can live several hundreds femtoseconds easily. So the kind of the dephasing time we observe here is around 500 femtoseconds.
Okay. Another question or two that actually will hold to the end because they're more general. So you should continue. This is a great start. Thank you.
Mm-hmm. Yeah. So yeah, exactly. So now I want a little bit, let's say, switch the gear or change the discussion a little bit. And in principle, I want to go into discussing this sensitivity of K-alpha X-ray emission to these structural dynamics. So initially, we were rather surprised by that because we were thinking mostly in terms of X-ray emission as being sensitive to the oxidation state and spin state. And we were surprised that we observed this kind of very clear signal that are perfectly in phase, right, with the structural signal in the X-ray scattering. With this, we started to think about chemical shifts that can be present in X-ray emission. And of course, chemical shifts in X-ray spectroscopy is a very long, it is the most fundamental concept in principle in X-ray spectroscopy and something that we are utilizing all the time when we are doing X-ray spectroscopy. So I made this slide to kind of like summarize or introduce in the most basic level how I think about a chemical shift in X-ray spectroscopy. So I think the simplest model that you can do is that if you can imagine that your molecule is a conductive sphere and there is a charge Q on this in this sphere. So then this charge Q, right, create electrostatic potential inside of the sphere that is proportional to the charge and inversely proportional to the radius of the sphere. So now you can, if you can imagine, if you have an electron inside of this sphere, right? So the energy this electron has due to this charge on this sphere is again, it's just the elementary charge multiplied by this electrostatic potential, right? And if you do this very simple formula, then you can see that of course the energy that this let's say the binding energy that this electron has, right? It's proportional with the number of electrons on this sphere, right? Now, if you increase the number of electrons on this sphere, you are decreasing the binding energy of the electron inside of the sphere. And so you can think of, right, if you reduce the molecule, your binding energy becomes smaller. If you oxidize your molecule, your binding energy becomes bigger. In a slightly more quantum mechanical formulation, but still in a very simplified way, you can write down the energies of the relevant states in this very simple way, where you just take into account, for example, some energy of the electron, for example, 1s and 2b electrons, and how these interact with some valence electrons, right? So the U. And from these very simple considerations, so like everybody knows, right, you can find that the binding energy, for example, of a core electron, for example, a 1s electron or 2p electron, right, that it's modified by the number of valence electrons at this atomic site. So again, if you imagine, if you reduce your molecule, your binding energy of your core level becomes smaller, and if you oxidize your molecule, the binding energy of your molecule becomes bigger. So in K-alpha X-ray emission now, the situation is a little bit different in the sense that in K-alpha X-ray emission, we are observing transitions between two core excited states. So between the 1s and 2p core excited states. So in there, the chemical shifts are significantly smaller than, for example, in photo emission or in X-ray absorption. The chemical shift that one observes in X-ray emission, they are, let's say, the leading term or the lowest order approximation, right? They are proportional with the difference of the core hole potential of 1s and 2p holes. So yeah, like I said, the chemical shift is of course a very long-standing problem, and this goes back to the work of Guy Siegban and even in the 1920s and around this time, and as it is also very well known that it's very difficult to quantitatively exactly calculate the binding energies at the absolute scale. However, usually when one thinks about chemical shifts, right, one thinks it very much in the terms of the electronic problem, that how to solve the, how do I count all the electronic interactions properly. So what we here now are thinking about is how does actually a molecular structure enters into this. So I think this is something that is not so often thought about, that if you can imagine that if you create core holes and you reorganize your electrons, right, how does a structure interacts to that? So and this is something that I think becomes relevant, right? If you do, for example, if you have a nuclear wave packet that is traveling, that is localized in space. So again, in this very simplified picture, I think the one way you could introduce, let's say, a structural coordinate to this problem is to take that, okay, it is the effective charge at the iron, let's say, that changes with the bond length. So in this case, right, the change in your X-ray emission energy is proportional with the change of the number of valence electrons at your with the effective, in principle, the effective charge of your of the iron. And for example, in a typical case where you have a bond that is chemical bond that is dominated, for example, by the ligand to metal charge transfer. So if the bond is shorter, you have more electrons at the iron site, and if you expand the bond, you have a less charge donation to the metal. So in this case, you expect to have, in this case, if you expand the bond, you effectively are like oxidizing the iron slightly. And this leads to the positive shift in the X-ray emission energy. One other way to think about this is if you think about in terms of potential energy surfaces. So if you think about the potential energy surface of, for example, the 1s and 2p core ionized states. So you observe a linear shift in the energy difference between these core excited surfaces if they are displaced with respect to each other. So this displacement is responsible to displacement of the bond length between these surfaces, leads to the linear shift again in the X-ray emission energy. So this kind of putting these two parts together, you can imagine that if 1s core ionized state, it has a stronger core hole potential than in the 2p ionized state, right? So this favors more shorter bond, and because of this interaction, you get a shifting of the X-ray emission energy with the bond length. So with this very simple discussion in mind, so I show again that, so here is again the data that we observed. So you see here the X-ray scattering signal that shows clear oscillatory behavior. And here is a trace of this X-ray scattering that is overlaid with the K alpha signal, which you see is perfectly in phase. So it's obvious for us that the structural oscillations lead to the that are related to the metal ligand bond length lead to the changes in X-ray emission intensity. So in order to understand this better, we collaborated with the theory group in Uppsala University. So the group of Markus Lundberg and particularly his postdoc Morgan Waher who did a high-level restricted active space self-consistent field calculation for us. So in principle, what they did is that they calculated for us K alpha X-ray emission spectra for different structures. And indeed, what they observed that the X-ray emission spectrum of this triplet metal-centered excited state, as you expand as you make the bond longer, the dominant, the effect that you see is just the shifting of the spectrum. For example, if you compare the structure of that corresponds to the ground state bond length to the optimal bond length of the triplet metal-centered excited state, you observe a shifting of about 0.3 eV, which then corresponds to the bond length expansion of about 0.12 angstroms. So using this shift of the spectrum, we see that this kind of, when we sit at the maximum of the ground state intensity, this kind of leads to the 10% change in intensity. And in this small region of the shift, we really see that the intensity modulation is really a linear. So if you can imagine now that if you have a coherently oscillating bond length, this really leads to a linear change in the change in intensity is linear with the structure, and this leads to this kind of oscillations in our data. Morgan Wacher and we analyzed the calculations that we did further, and this is in our follow-up paper in the structural dynamics. So they really they in principle calculated the potential energy surfaces for the valence state, for the 1s core ionized state, 2p core ionized state, and they really observed that, of course, first, if you look at the core ionized states with respect to the valence state, so the core ionized states, both 1s and 2p, have significantly shorter bond lengths. But in addition to that, there is also a bond length difference between the 1s and 2p core ionized states. So this displacement of the 1s and 2p core ionized states is that causes this linear shift that we observe, right? So this is the sensitivity, where the sensitivity to the structure comes. So in our experiment, you can imagine that as we are oscillating on this valence potential energy surface, the X-ray emission that we observe, right, follows this motion because the core ionized surfaces are displaced. If the core ionized surfaces would be perfectly aligned on top of each other, there would be no sensitivity of XAS to the structure. And in addition, they analyzed the calculations that they did further, and they found that, of course, the picture that I presented a few slides ago, it's a simplified picture. There are a number of different other electron-electron interactions that change, that are different in 1s and 2p core ionized states. For example, they found that the 3s and 3p electrons contract significantly. They found that there are different final state effects. For example, the 1s and 2p states have different covalences actually at the same bond length. So this is described in this structural dynamics paper. So with this, I come to the summary of my talk. So here on the left, it's a kind of a summary figure. So what we observe is that we observe a kind of a non-trivial electronic population dynamics. So we observe branching between the MLCT and triplet metal-centered excited state. And importantly, in the triplet metal excited state, we observe this kind of coherent nuclear wavepacket dynamics. And this wavepacket dynamics, we don't see it only with the X-ray scattering, but we also see it with the X-ray emission. And we think this is because that your 1s and 2p core ionized surfaces are slightly displaced with respect to each other. So they feel these changes in the effective charge at the iron slightly differently, and this leads to the sensitivity, structural sensitivity. And yeah, with this, I would like to acknowledge all my collaborators. So so this was work, yes, I did in the group of Kelly Gaffney, and important contribution to this, of course, comes from the Lund University, who are synthesizing these molecules and who are actively investigating these systems, and who are really driving this field right now. Important contribution to this work also comes from the group of Martin Nielsen from the Technical University of Denmark, who are the X-ray scattering experts, and of course the George Vanko group in Hungary, who I think it was George's idea to actually use to also put in the K-alpha X-ray emission detection. And of course, I have to thank all the scientists at the LCLS and the SSRL who were very without who one cannot do this beam times. And of course, very important contribution was also our theory collaborators in Uppsala University. So, and with that, I thank you for your attention. So.
Thank you. It's very interesting. We'll start with some questions. Yulia Pushkar, you had a question?
Yeah, hello, Kristjan. I have several questions, but I'll try to be brief. So first of all, we also looked at the effect of the structure. So we have paper in 2017 in Journal of Physical Chemistry Letters, where we just changed one proton. So we removed one proton from one OH and made a manganese double bond oxygen. And we showed that there is a pretty measurable effect on K-beta, manganese K-beta line. So we kind of saw it not in a dynamic case, but in static case. But I have several questions to you. So your K-alpha versus K-beta. So you didn't detect oscillations in K-beta. Do you think it's a signal to noise ratio issue, or you think they are not there?
Yes, shortly, I think it's a signal to noise issue, but of course, yeah, I cannot be certain right now. In this experimental configuration that we did, if you look at the time delay traces of K-beta, the signal to noise is about 10 times worse than in K-alpha. So this is really on the limit. So in the K-alpha traces, I think the oscillations that we see are about 1% of the total signal level, and our signal, the signal to noise is really around like per mil, few per mil. So in the K-beta, it's really, I would say it's a signal. One would need to improve the signal to noise of K-beta in order to say something for sure.
But on the other side, for K-beta, you have a full spectrum, and here you just have one energy position. Okay,
yeah, absolutely, good.
Yeah. So my next question is, why normal metal to ligand charge transfer, so your MLCT, does not do this dynamic? Why it has to be, you know, metal charge triplet to show us this dynamic?
It's simply because the charge transfer state is not displaced significantly from the ground state structure. So as we excite to the charge transfer state, there is no significant metal ligand bond expansion. So the triplet state, because in the triplet state you're actually populating this antibonding EG, the bond length significantly expands, and you need this kind of, if you think about this, it's actually rather significant bond length expansion, right? That's it's more than 0.1 angstrom that actually takes place, and you need this actually significant expansion of the bond to see this effect.
Yeah, so I was also very impressed that you have calculations for K-alpha X-ray emission spectra, because in our case, like for us, we simply analyze like a spin density distribution, and from this we infer the direction of the shift. So my question to you, for those calculations, did you like take into account entire molecule, like all the ligand, or it was somehow simplified? So what was the level of calculations?
Yeah, I'm sure that my collaborators in Uppsala can say much more about that. But in principle, yes, we took into account the whole structure of the molecule. So it's it's a ab initio calculation. So it's a restricted active space, self-consistent field calculation. So so it includes also the multiplet effects and everything these. And so yeah, and you really put in the structure. We put in the molecular structure of the ground state, of the triplet metal centered excited state, you know, with the different bond length, calculate the X-ray emission for that.
Okay, thank you.
All right. Another question. You gave the qualitative description of a motivation for the K-alpha shift on the basis of screening effects.
Yes.
Then I understand this is intended to be qualitative. But when I look at the results, I feel that I suspect the symmetry change is at least as important as the charge effect. And I motivate that because when you look at iron compounds at high pressure, and you start shortening the bond lengths, I don't think you see K-alpha shifts.
Ah, really interesting.
Yeah,
I'm not aware of. Yeah, I mean there is indeed a symmetry change also, right? You can think of this triplet metal centered state as a like a Jahn-Deller active. There is a reduction in symmetry.
I'll give another argument.
How significant it is. Yeah, I mean, yeah, it's I wonder if there is some clear way to. Of course, one could do more calculations, right? With structure that are more symmetric.
Yeah, you could force all 6 ligands to breathe in the simulation.
Yeah, yeah. I mean, I don't know. Yes, of course of course this yeah, chemical shift argument. It's very qualitative, and however, I see that it kind of gives the right result. So
well,
so yes, it's yeah.
I also the other reason I'll bring up, reason to be a bit skeptical about it, is there ought to be much bigger effects on the 3p than there are on the 2p, because more volume of the valence electrons is leaks within the 3p than within the 2p, and yet you don't see large changes. And again, in pressure studies, you know, they see spin effects, but they don't see any direct effect of compression per se. So that's what makes me suspect that it's more complicated than just a.
But I wonder in the pressure studies, like how big is the bond length change? Exactly.
It's a fair question, and certainly in shock compression or more extreme conditions.
Because I think we have a much bigger bond length changes than in pressure studies.
That's fair. All right, we'll move on. Jacinto, you had another question?
Maybe I misunderstood a little bit what you said about this linear relationship, because I mean you're measuring the difference between the 2 electronic levels as a function of displacement, and this is what gives you the shift. Mm-hmm. But why would it be linear? I didn't understood that part.
Yeah, it's yeah. In principle, if you think that. Right, if you take 2 harmonic surfaces and you displace them horizontally, right? And then if you take the difference, you see that this difference changes linearly, right? So the displacement, you can think of displacement as a linear vibronic coupling.
I mean, I would expect that it would follow basically. The distance between the 2 curves would follow. It's basically a compromise between the displacement and the shape of the 2 curves. So it's, I mean, you don't have 2 perfect harmonics.
I mean, in this argument, I assume that the force constants are the same. Yes.
Okay. Okay. So then.
So this is something also that we see from our calculations. that we see that if you look at if you compare the valence surface with respect to the core ionized surfaces, we see that the core ionized surfaces, the force constant gets bigger, right? The surfaces, they become more steep, right? But if you compare the 2p and 1s surfaces, they have the nearly identical curvature, the force constant. So it's really just the displacement that really shows up.
Okay. All right, Cheng Jun, you have a question?
Yeah, hi, thank you. Hi, Kristjan, great talk. I will keep my question brief. In one of the graph, you show the simulation and the experimental is matched very well. I just, for the K-beta emission intensity, I just wondering what's the oscillation? It's about 200, 250 femtosecond. What the oscillation mean? Well, what's the scientific meaning?
Yeah, it's so if I fit the period is about 278 femtoseconds.
Yeah.
And your question is like, what is the
oscillation? Yeah, which kind of the science, which the physics drive the oscillation of the K-beta emission, K-alpha emission?
Yeah, so yeah, I mean, my explanation, right, is what makes the K-alpha sensitive is the fact that right, the 1s and 2p surfaces are displaced with respect to each other, so they have effectively slightly different bond lengths, and I would argue that one could connect this to the fact that right, as you change the bond length, you have a change in the effective nuclear charge on the metal. And because the 1s and 2p have a different core hole potentials, this leads to the shifting. But of course, there are, that's, let's say, simplified picture.